So thank you very much, Alexandre, and many thanks to Jean and Alexandre for organizing these meetings or for the invitation. I'm going to speak about the Pleijel nodal theorem and related results, and present some work which I done alone and in collaboration with Gittins, but I want to also kind of survey the topics, so there will be other results, historical and more recent ones. First, the setting. So we look at a domain, by which I mean simply an open-bounded and connected subset, either of Rn or of an n-dimensional Riemannian manifold, and look at Laplace or Laplace spectrum operators in those in these domains omega, and to make it a self-adjoint operator, we specify a boundary condition. I look only at classical ones, Dirichlet Neumann or Robin, with normal derivative plus HU and UH real valued function on the boundary. Well, under reasonable regularity assumptions, we have then a self-adjoint operator with compact resolvent, and we have a sequence of the spectrum is a sequence of eigenvalue tending to plus infinity. So just about the notation, I'll try to, in general, call them a mu k, and start the enumeration at k equals 1. Except for the Dirichlet case, well, I'll use the notation lambda k. And also, for those problems, we can choose a basis of real valued eigenfunction and limit everything to considering real valued functions, which is what we are going to do. What we're interested in are the nodal properties of these eigenfunctions. So we just recall that the nodal set is a zero set of an eigenfunction, and what we are really interested in are the nodal domains, which are the connected component of the complement of the nodal set. To have the right picture in mind, we can look at the square. I've drawn some nodal sets for the eigenvalues of for eigenfunction of the Dirichlet Laplacian, and they consist of union of nodal lines which divide the square into nodal domains. I'll get back to that picture. The thing we are really interested in this talk is once we've specified a domain, a boundary condition, and chosen an eigenvalue, what can we say about the number of nodal domains for an associated eigenfunction? This is the question that we ask. And there are some classical results which make us hope that we can say something meaningful. Of course, the first one is the 1D case, where we look at Sturm-Liouville differential operator on a segment AB, regular Sturm-Liouville operator with separated boundary condition, to simplify. And in that case, the spectrum is a sequence of simple eigenvalues tending to plus infinity. And an associated eigenfunction has k minus 1, 0, since we start the enumeration at 1, inside the segment AB, which means that it divides the segment into k nodal domains, which means that, well, in that case, we have completely solved the problem. Of course, this is quite...
Corentin, may I ask a question?
Yeah, sure.
What is a separated boundary condition?
Oh, I just mean that the condition at A, for instance, only involves the values of the eigenfunction at the point A. A periodic boundary condition is not going to work. I mean, you have to modify the statements a little bit. That's the only thing. Okay, so then there is a partial generalization to higher dimension proved by Courant in 1923, where he used actually the min-max principle to prove that. And it tells us that in these classical eigenvalue problems, which I described in the previous slides, if you choose an eigenfunction associated with mu k, you will have at most k nodal domains. So you get an upper bound on the number of nodal domains. And since this is a property which will recur in the rest of the talk, I will introduce a definition and say that an eigenvalue mu k is Courant sharp if it has some associated eigenfunction with k nodal domains, so that Courant upper bound is reached. Now, if you want to get now a lower bound, well, you can, there is some sort of trivial one when you say that, okay, an eigenfunction associated with mu one does not change sign, and therefore an eigenfunction associated with an higher eigenvalue has to be L2 orthogonal to it, so it has to change sign, so that the scalar product vanishes, and to have at least two nodal domains. But this is, I mean, a trivial lower bound, and in general, you cannot hope to get any better. In fact, at the same time, a student of Courant, Anthony Stern, constructed a counterexample for the Dirichlet Laplacian and found a subsequence of eigenvalues, so tending to plus infinity, with an associated subsequent sequence of eigenfunctions having exactly two nodal domains. So you cannot really go beyond the trivial lower bounds in higher dimensions, but still you can ask yourself in how frequent is that? Can you get, is there infinitely many eigenvalues which are Courant sharp, or are most eigenvalues Courant sharp even? And this is where Pleijel's results come into play. He showed that the answer is negative. So he considered the Dirichlet Laplacian in a domain in R2 and showed that for this there are only a finite number of indices for which lambda k is Courant sharp. And actually what he proved is more specific. And to state it, I introduce the nodal count, mu k, which has defined either maximal number of nodal domain for an eigenfunction associated with lambda k, or more generally mu k. And I study the ratio mu k over k. By Courant, we know that it's at most 1. But what Pleijel proved is that asymptotically, it's bounded from above by some universal constant, which is strictly smaller than 1. And, well, you can generalize it to higher dimension than R2. And what you get is that the same type of asymptotic upper bound with a constant gamma n, which which depends only on the dimension and is strictly smaller than 1.
Sorry, Corentin, what is J square?
This I will tell it right away. So what's this constant gamma n in the, let's say, general case? I've written a 2 pi to the n. The first eigenvalue of the unit ball in Rn to the power n over 2 multiplied by the volume of the unit ball squared. So this will come from the proof. I'll show that in a minute. But here, I mean, these is things that you can compute explicitly, and they involve gamma functions, values of the gamma functions, and zeros of Bessel functions. In the case n equals 2, this constant j is the first positive zeros of the Bessel function j0, which, I mean, is strictly greater than 2, so you get a constant which is smaller than 1, which actually is true for n equals 2 or higher. And doing more work, Bernard Helfer and Michael Persson-Sundquist showed that actually this gamma n constant is exponentially decreasing with n. In particular, it's always strictly smaller than 1. well, the proof is actually very simple, and also it's the basis of a lot of the further work, so I will give it now. And it will explain where this kind of strange constant comes from. What you do is that you choose an eigenfunction u associated with lambda k with a maximal number of nodal domain, uk, the nodal count. And then you pick some nodal domain, the I. And then you have to realize that there is a connection between lambda k and the I, which is you satisfy the eigenvalue equation with lambda k inside the I. It does not vanish inside the I, but it vanishes on the boundary. So this in the end tells you that lambda k is equal to the first Dirichlet eigenvalue of the I. So then you look at this product, you substitute lambda 1 di for lambda k, and you apply Faber-Cron inequality. This scaling invariant product is minimized for a Euclidean ball. And this gives you, well, something which depends only on n. Then you sum over all possible nodal domains. On the left-hand side, you get the total volume of the domain, and you recover a nu k on the right-hand side. So you get an upper bound for nu k, which depends on lambda k. We'll use it later. But at this point, what we're interested in is estimating this when k goes to plus infinity. And this you do by Pleijel law. And when you divide by k, you get the upper bound with the constant on the right-hand side. That something I want to point out is that, as I've stated it, the argument only works for the eigenvalue, the eigenfunctions with Dirichlet boundary condition. And this you can see on this picture, for instance, because the crucial point is that lambda k is lambda 1 of the nodal domain. And if you have a nodal domain like this, which is bounded by your nodal line, everything is fine because the eigenfunction will vanish there. But if you have an nodal domain touching the boundary, part of the boundary of the nodal domain is contained in the boundary of omega. So if you look at the Dirichlet case, again, everything is fine. But if you are in the Neumann or Robin case, the eigenfunction does not vanish here, and you cannot use Faber-Cron inequality. Still, you can extend the proof beyond just domains in Rn into manifolds. And this was done by Petre almost immediately, but in a setting which is a bit restricted, and much more generally by Berard and Meyer in 1982. But they had to assume, well, they considered manifolds, for instance, compact manifolds without boundary, or domains in manifold. But if you have a non-empty boundaries, you have to assume that you are in the Dirichlet case. And well, the difference from the previous proof is that you cannot use directly Faber-Cron inequality. You have to prove a Faber-Cron inequality adapted to your setting, which they did. So you deduce it from an isoperimetric inequality by a symmetrization argument. And the bulk of their paper was proving an isoperimetric inequality, which is asymptotically close to the Euclidean case for sets of a small volume. And doing that, you can extend Pleijels' argument and get the same asymptotic upper bound. So as I explained, there is an issue for the Neumann boundary condition, but still in Pleijels' paper, there is a study of the square with a Neumann boundary condition. And he showed that the same asymptotic upper bound holds. The proof starts in the same way. You pick an eigenfunction associated with nu k with the nodal count of nodal domains. And then you divide the nodal domains into two classes. The interior domains, which do not touch the boundary, and the boundary domains for which the boundary of the domain is partly contained in the boundary of the square. And you have to control well, you have new 0, k interior domains, new 1, k boundary domains. You have to control this new 1, k somehow. And this you can do. I mean, the crucial observation is that the restriction of an eigenfunction to a side of the square is a trigonometric polynomial of degree at most square root of mu k. So that, well, if you think about it, this tells you that these boundary domains, their number is controlled by square root of mu k. And by Weil's law, this tells you that the number is negligible with respect to k. So they don't count. Then you just have to bound the number of interior domain, and for that you can use the same argument as before. There's no difference with the Dirichlet keys. Well, okay, this is kind of an overview of the classical results, and now I want to move to more recent results, and the first one is the first results, which is somewhat general in the Neumann case. It was proved by Poterovich in 2009, and it applies to domains which are two-dimensional with a piecewise analytic boundary. To do that, you use a result by Toth and Zeldich, which estimates for such domains the number of zeros of a Neumann eigenfunction associated with mu k on the boundary of the domain. And you get an estimate from above by some constant depending on omega, but only on omega, not on k, and square root of mu k. And then using that, you can prove that the asymptotic upper bounds holds for Neumann eigenfunctions for these types of domain. Of course, you still want to generalize this, and you can do that in several directions. You can increase the dimension. You might want to look at less regular boundaries and also more general boundary conditions. So I managed to do that by changing point of view slightly. So I want to explain this. This paper that was published last year, but the result is older than that. It applies to domains in Rn with a C11 boundary and to the Robin Laplacian. I impose a boundary condition of this type where h is a function defined on the boundary of the domain, which is Lipschitz continuous and non-negative. In particular, this contains a Neumann case because you can take h identically equals to 0. And the result is not surprising. It's simply that the same asymptotic upper bound with the same constant as before holds. To do the proof, you go through similar steps, and you again want to divide the nodal domain into two classes. But instead of looking whether or not they touch the boundary in a strict sense, what you are interested in is in a given nodal domain, where is the L2 norm or the mass of the eigenfunction located. You want to distinguish between it's located mostly inside omega, or there is a non-negligible amount of mass close to the boundary, which is kind of natural if you want to apply variational arguments. Well, still you have to make it explicit, and to do that you consider a tubular neighborhood of the boundary. The most important one is the inner tubular neighborhood with a radius r, and this radius you make it depend on a parameter delta, which you have to adjust. Associated with this, you construct a smooth partition of a unity with a function phi0 supported inside, functions phi1 supported close to the boundary, satisfying this identity inside omega, and some uniform bound on the gradient of the order of 1 over delta. Once you've done this, you consider an eigenpair for the eigenvalue problem. So mu u, you define the product phi 0 u, phi 1 u, so localized inside or close to the boundary. And by construction, for each nodal domain, you have this identity. So the L2 norm inside the nodal domain comes from one contribution of u0, so the inner contribution, and one contribution of u1, the boundary contribution. And once you've done that, you can give a precise meaning to the idea I introduced at the beginning. You fix some threshold, epsilon, between 0 and 1, and you say that you have a bulk domain if 1 minus epsilon, a proportion 1 minus epsilon of the L2 norm, at least, comes from u0, and a boundary domain if more than epsilon of the L2 norm comes from u1. Then you consider the number of bulk domains, the number of boundary domains, and you estimate them separately. I mean, heuristically speaking, you want the number of boundary domain to be negligible for large eigenvalues, and therefore you have to shrink this the size of the tubular neighborhoods. So you choose them of size 1 over theta, mu theta, with a theta positive exponent to be determined. Well, if you follow Pleijl's proof, you obtain this upper bound for the number of bulk domains, which is almost the same as before, except that you have this factor depending on epsilon in front of the eigenvalue. You have this additional term coming from the multiplication by a cutoff function.
Can I ask a question, Corentin?
Yes, of course.
Do you also use Fabre-Kranz inequality in these steps?
Yes, in fact, you use Fabre-Kranz inequality in the sense that you will have a Rayleigh quotient that you need to estimate from below, and at this point you use Fabre-Kranz inequality. You always use Fabre-Kranz inequality in those estimates. So you see that if you choose here theta smaller than 1 over 2, this term would be negligible with respect to the main one in mu. And if you want to control the number of a boundary domain, and this is a slightly more difficult. You can use a reflection argument through the boundary, so that you have a function which will vanish on the boundary of your reflecting domain, and then you again use Fabre-Kranz inequality to get an upper estimate in u1, which will come with a very bad constant. If you have something c which can be very large, you have this 1 over epsilon, which is even worse. You have term of the same order as before, but what will play a role is the volume of the tubular neighborhood around the boundary, which is going to be of size epsilon and of size, delta, and therefore is going to shrink with large eigenvalues. Okay, so if you choose theta between 0 and 1.5, and if you consider mu going to plus infinity, you get the right order of magnitude. I mean, you can be a little bit more precise. You consider a sequence of eigenfunctions associated using mu k with the maximum number of nodal domains. Then using that estimate and Weis law, you get that the number of boundary domains is negligible with respect to k. And you also get an upper bound on the number of bulk domains. So putting all this together, you get an upper bound of the ratio nu k over k asymptotically, which is the Pleijel constant times some epsilon dependent factor, and you don't really care about this because you can choose epsilon arbitrarily at the beginning, so you make it go to 0 and you get the right asymptotic upper bound. So I'm going to leave aside asymptotic upper bounds for the moment, in a way, because so far what we have done is trying to extend this asymptotic upper bound to larger class of domains, larger class of boundary conditions. But you can look at the problem in a slightly different way. And this is what I want to consider now. You can look at it in the following way. Assume that you have a domain omega and a realization of the Laplacian which satisfies the asymptotic upper bound, which falls under the one of the previous results. Then you know that there are finitely many Courant sharp eigenvalues. But you can ask yourself how many, and it would be even better to know what exactly are the Courant sharp eigenvalues. If you want to know that, you have to know something about omega. And again, in his paper, Pleijel started analysis of this type for the square with a Dirichlet boundary condition. And I'm going to speak about the start of this analysis because it's an idea which is used in other cases in further development. I mean, what he does, you can present it in this way. You introduce a counting function of the squares, so the number of eigenvalues, n lambda is a number of eigenvalues strictly smaller than lambda. And for the square, this is simply counting the points with positive integral coordinates, which are at a distance less than square root of lambda from the origin. This you can estimate by some geometric argument. And in particular, you have this strict lower bound. Of course, this is only valid for the square. But this is kind of a general idea. You want, when you try to do something like that, you want to get a lower bound for the counting function and not just an asymptotic estimate given by Bayes' law. Then you have an argument which is also rather general. You assume that you have a Courant sharp eigenvalue, then the nodal count is k by definition, and lambda k is strictly greater than lambda k minus 1. And therefore, the value of the counting function is k minus 1, and this quantity is 0. In particular, it's non-positive. But for that, since you have a lower bound for the counting function and an upper bound for new k coming from Pleijels' argument, which depends on lambda k, you get a lower bound for this quantity. You get a lower bound for this quantity, which I've written here, and which goes to plus infinity when lambda k goes to plus infinity. And therefore, since it has to be strictly smaller than 0 for Courant sharp eigenvalues, this gives you an upper bound for Courant sharp eigenvalues. In that case, a Courant sharp eigenvalues has to be smaller than lambda k, and therefore you are reduced to a finite number of cases to study. Now, with more work, in that case, you can show that the only Courant sharp eigenvalues are the trivial ones, lambda 1 and lambda 2, and the eigenvalue lambda 4, which is actually quite general. Generally speaking, in all the examples which you can study explicitly, you have very few Courant sharp eigenvalues. Now, moving on to more general results, what you want to get is some sort of geometric control on the number of Courant sharp eigenvalues, which is of the following type. You define, so I'm going to speak about the Dirichlet case here. You consider a domain in Rn and you define the largest index k such that lambda k is Courant sharp. You denote it by kd of omega. And what you want to get is an upper bound on kd of omega using a few geometric characteristics of omega. And as I just explained, the crucial step for that is getting a lower bound for the counting function of the Dirichlet eigenvalue problem on omega. So this was achieved by Pierre Bérard and Bernard Helfer and by Michael van den Berg and Cathy Gittins by different methods. So for instance, in the Bérard-Helfer result, they considered a domain in R2 with a C2 boundary, although their method is more general than that, as they say. And they got a bound involving the volume of omega, the length of the boundary, and a geometric quantity called the cut distance. Also, they used Safarov's version of Bayes' law to get this estimate. And in the van den Berg and Gittins paper, they considered an open set of finite measure in Rn. And they showed that kd of omega is controlled by some constant times volume divided by epsilon omega to the power n, where epsilon is a geometric quantity involving the volume of tubular neighborhood of the boundary somehow. I want to also to point out one corollary, which is stated in their paper, the case where omega is a convex domain, because there they get an upper bound with some explicit constant depending on the dimension, and the isoperimetric ratio, so the n-1 dimensional measure of the boundary to the n divided by the volume of the set omega to the n-1, which is actually quite interesting because this gives you some sort of inverse information. There are quite a lot of results which show that if you take a domain which kind of shrinks or degenerates to a very long and thin domain with Dirichlet boundary condition, then we'll have a lot of Courant sharp eigenvalues because the problem degenerates the eigenvalue problem for the Laplacian degenerates to some sort of Sturm-Liouville problem. But here you have a converse implication. If you have a convex domain with some Courant sharp eigenvalues which is high in the spectrum, this inequality tells you that, which tells you that kd of omega is large. This inequality tells you that the isoperimetric ratio also has to be large, and therefore the domain has to be rather long and thin. But all this works in the Dirichlet case because it involves also an upper bound for the nodal count, which, as I explained before, works for the Dirichlet boundary condition. So Cathy and I tried to extend it to a Neumann and Robin boundary condition, but then we had to work to obtain these estimates on the nodal count. The estimates on the counting function, they were basically the same. And by the way, in this paper by van den Berg and Gittins, they relied on a Dirichlet bracketing argument to get these estimates. So Cathy and I considered a domain with a C2 boundary, Neumann or Robin boundary condition with a non-negative function h. And we obtain several results. To simplify, I will present the results for a convex omega in 2 dimensions. So the dimension 2 hypothesis is not so important, but the convexity hypothesis is, because the results are less clear-cut if you just if you do not assume it. So we denote by A the area of the domain, by L the length of the boundary, by R the isoperimetric ratio, L over square root of A, and we define a kappa plus at the maximal curvature of the boundary of omega. What we got is that there exists some constant C, which is certainly not optimal in what we did, but which is explicit, and which is independent of omega and H, such that if mu k is an eigenvalue for this problem, which is Courant sharp, then it's bounded by an expression of this form. So C over A times this scaling invariant factor, which involves the area, the maximal curvature to the power of 4, and the isoperimetric ratio also to the power of 4. And then this is for the eigenvalue. For the index, again, as before, we define kr of omega h, which is the highest k, the largest k, such that mu k is Courant sharp. And this we can bound from above by some constant C prime times this same scaling invariant factor. I must say that going from here, so theorem 1 to theorem 2, is not completely straightforward, and this is one of the points where we use the convexity hypothesis. So how do we do that? Well, the lower bound for the counting function is the same as the Van der Bellen Gittins paper. This is not a problem. The problem is getting an estimate for the nodal count, and for this we kind of run the proof that I presented for the Robin case, but we keep everything explicit, and we try to get estimates which are explicit in the geometric parameters of omega. And to do that, we parameterize the boundary by, so in dimension 2, we parameterize the boundary by arc length, and we parameterize the tubular neighborhood of the boundary by arc length and by a normal coordinates. This gives us an explicit diffeomorphism, which involves the curvature. This is where the curvature comes into play. And by constructing a cutoff function in these coordinates and using explicit estimates, in the end, we can get theorem 1. For theorem 2, we need some additional result, which is that we can bound the index k by the eigenvalue mu k when we have a convex domain. And this is not clear in general, because for Neumann boundary condition, we can have a lot of very small eigenvalues, but with the convexity hypothesis, this cannot happen. And the proof is based on a Neumann bracketing argument and on isoperimetric, an eigenvalue inequality by Penn and Weiberger for the convex set, which tells you that mu2, the second Neumann eigenvalues, the first one, which is positive, is bounded from below by pi squared divided by the diameter of omega squared. And this allows you to go from theorem 1 to theorem 2. Okay, so we have this asymptotic upper bound, we have this kind of geometric control on the number of Courant sharp eigenvalues. There is a last thing that I want to speak about, which is the connection between this asymptotic upper bound by Pleijel and a minimal partitions problem for eigenvalues. This I will try to present in the two-dimensional case and for the Dirichlet eigenvalue problem. And my presentation will be a little bit simplified, but these are ideas which I learned from Bernard Helfer. We consider what I call a spectrally balanced partition of omega, which is simply a spectrally balanced n partition of omega, which is simply a family of n open sets, open subsets of omega, which are mutually disjoint, and for which the first Dirichlet eigenvalue is the same. This common value, we call it lambda of large lambda of the partition, and we call it the energy of the partition. And the minimal energy is going to be the infimum of the energy of the partition when the partition are taken in the class of spectrally balanced n partition. So the existence of the minimizers for this problem and their fundamental properties were studied by Bernard Helfer and Thomas von Ostenhoff. Thomas von Ostenhoff and Susanna Terracini in the 2009 paper, although they presented it a bit differently. What I'm interested in here is the connection with Pleijel argument. Because in Pleijel argument, you want to bound nu k over k. So to do that, you can split the ratio nu k over k as nu k over lambda k and lambda k over k. And the lambda k here and there, you think about it in a different way. Here you are thinking about it as an eigenvalue and you will use Bayes' law. But here you realize that if you take an eigenfunction with nu k nodal domains, and if you consider the family of all its nodal domain, you get a spectrally balanced partition with n equals nu k. And therefore lambda k is at least L nu k of omega. So you can get an upper bound in that way. And taking k going to plus infinity, you get an asymptotic upper bound of nu k over k, which well involves this term you estimate by Bayes' law, and this terms you bound it from above by this asymptotic lower bound for the minimal energy divided by n. Now, if you go back to Pleijels' estimate, it doesn't really involve actually the fact that you are looking at nodal domains. You only consider the fact that you are looking at subsets of omega for which you have the same lambda 1 on each of them. So it's actually a statement somehow about these spectrally balanced partitions. And Pleijels' argument actually gives you a lower bound for this Ln omega divided by n, which you get using Fabre-Cohen inequality, and which is volume of the unit disk times lambda 1 first Dirichlet eigenvalue of the unit disk divided by the total area of the domain, which is of course explicit. And this somehow is the right way to look at improvements to Pleijels' result were made by Bourgain and Steinerberger in 2013. What they get were actually improvement on the lower bound of this minimal energy for partition of n partitions of omega. Because if you use Pleijels inequality, you try to minimize the energy by making each element of the partition as close as possible to a disk. But if you do that, you are not going to include all the area of omega. So there is a competition between being close to a disk and leaving as few gaps as possible. And taking this competition into account, they managed to improve the lower bound for this Ln omega energy. So the improvement by Bourgain is explicit, and I think it's of the order of 10 to the minus 9, so it's very small, but it's real. And for Steinenberger, it's unfortunately non-explicit because it uses quantitative Faber-Cohen inequalities which involve non-explicit constants. And similar things, similar results, also non-explicit, were obtained in n-dimensional manifolds by Donnelly. So you see that if you increase the lower bound for this, you decrease the upper bound for, you decrease the asymptotic upper bound for nu k over k. So you improve Pleijels result. And then you can wonder how much you can improve, which in the end tells you how much you can push Pleijels' argument. Well, there is a conjecture about the optimal way to get a partition of omega, which was formulated by different people in slightly different contexts. And the conjecture is that the best way to do that when n is very large is to have a regular hexagonal tiling. This will be asymptotically optimal, which tells you that Ln omega over n, when n goes to plus infinity, will go to this quantity involving a regular hexagon. So if this was true, this would give you an asymptotic upper bound of Pleijel type, where you would replace the disk here in the denominator by a regular hexagon. So it would decrease the upper bound. And since that would be the optimal way to partition omega, this is the best that you can hope for using Pleijels' argument. But of course, Polterovich formulated a conjecture which, I mean, has been supported by a lot of examples, that actually the optimal asymptotic upper bound is not when you put an hexagon here, but when you put a square. So it would be a 2 over pi, which is still lower. And this is optimal because you can make explicit computation for a rectangle with sides a and b such that a squared over b squared is irrational. And you see that the lim sup of nu k over k is, in that case, is explicit and is 2 over pi. So you cannot do better. And the conjecture is that this is actually the optimal upper bound. Now, this was supported by a completely different method from Pleijel, by Jung, who considered Dirichlet eigenfunction is a square and restricted the nodal count to eigenfunction without singular points on the nodal set, and showed that for the restricted nodal count, Polterovich upper bound holds, which is, I mean, of course, it's a restricted setting, but on the other hand, it showed that even using completely different method, you get this result. So this seems to be the right conjecture, but to prove it in general is extremely difficult. And there is one last thing that I want to mention. Beyond the Laplacian in domain, the Pleijel asymptotic upper bound also holds for eigenfunctions of the Schrödinger operators in Rn. For so of the type minus Laplacian plus Vx for several choices of V, for instance, for possibly anisotropic harmonic potential, for classes of radial potential, which includes the Coulomb case, so the Schrödinger operator for the hydrogen atom. This was proved by Charon and Philippe Charon, and by Philippe Charon, Bernard Helfer, and Thomas Hoffmann-Ostinov. But in their proof, it uses facts about the nodal domain of polynomials on algebraic surfaces. So this is a bit rigid, and one would want to extend it to a larger class of potential using variational arguments. So we are working on it with Philippe, and we now have good hope to get more general results and to extend the validity of this asymptotic upper bound to a larger class of operators. And I hope that I'll be able to speak about it at some point. I'm going to stop there. Thank you very much.
Thank you very much for the very nice talk. Let's thank the speaker. Yes, actually.